Hi, and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about acceleration. And in this video I'm basically going to introduce this concept of acceleration and then kind of explain what it does. This is a fairly straightforward video in some sense, but in another sense it's one that those of you taking physics for the first time should pay a special attention to, because I also want to point out a few things about acceleration that are misconceptions. Namely, how is it actually related to velocity? Because a lot of people will use the two terms interchangeably, and they're not interchangeable at all. They actually mean different things. So let's get into the video and let's learn a little bit about acceleration. So let us begin by a little review again. So recall that we've previously defined the velocity. So what is the velocity? Well, it is the rate of displacement, or put differently, it's the rate change of position. That means that we can define it as delta x over delta t, or delta y over delta t, or delta z over delta t, if we're looking in one dimension. So this defines velocity. And we've even discussed a little bit about what happens if you have a constant velocity motion. So what does acceleration add to this picture? Well, acceleration is defined as the rate change of velocity. That means that if we want the average acceleration, the vector for average acceleration is defined by delta v, change in velocity, over delta t, change in velocity per unit time. Now notice that the change of something is not the same thing as that something. These, for example, have different units. Velocity is given in meters per second. Acceleration is given in meters per second, or in other words, meters per second squared. They are not describing the same thing. Now they are related to each other. This equation relates them. We'll even be able to kind of, by analogy to the motion with constant velocity video, we can get a relationship between velocity and acceleration. For motion with a constant velocity, we could write that the position, if we're moving x's position as a function of time, or if you prefer just simply x, was equal to the velocity times the time plus the initial position. Okay, so the analogy that we might use here is if we want to have constant acceleration, for constant acceleration, that is the same thing as constant change in velocity per time. We should be able to write that the velocity as a function of time, which we now would represent as v, would be equal to the acceleration times the time plus the initial velocity. Okay, so acceleration times time plus initial velocity. Note that up here, when we're talking about motion with constant velocity, we could insert a little subscript I to say that this is now the initial velocity. And I'll even do that in a different color to note that this is the initial velocity, but when this thing has been moving with constant velocity, the initial velocity is the velocity at any later time. If you have a constant acceleration, then that means that the initial velocity is not going to be the velocity at some time later. Okay, so these two are different situations. Another thing to note about acceleration is that, as I've said before, it's a rate change. So you can get it from the velocity versus time graph. So again, recall that for a position versus time graph, the slope gave us the velocity. So if this is the time and this is the position axis, and I have a graph that does one of these guys, then if I want an average velocity between 2 points, then I pick a line that goes straight through the 2 points, and the slope of that line would be an average velocity. So this is average velocity, or slope is average velocity for the 2 times chosen. So this might be time final and time initial. So this is average velocity for interval between the initial and final times, or Ti and Tf. On the other hand, if I pick a specific point on this line of best fit, say right here, and we just call this like T sub A or something like that, and I make a tangent line. So this line is tangent at that point. Whoops. Slope of this tangent would be the velocity at time ta. And again, to get that slope for that tangent line, you would draw the tangent line, and then you would basically pick 2 points somewhere on the line and use rise over run to get the slope. Nothing fancy there, it's just simple basic algebra. So what is the equivalent to this for acceleration? Well, for acceleration, you would need to have instead a velocity versus time graph. So time and velocity. So with this velocity versus time graph, if I pick 2 points on it and draw a line, straight line that connects the 2 points, then this slope would be an average acceleration. Again, if I have a velocity versus time graph, the slope will give me an acceleration. And if I pick 2 points that are on the curve for velocity versus time, and I draw a straight line connecting them, then the slope of that straight line will be my average acceleration for the interval from initial to final time. And in a like manner, if I pick a single point and draw a tangent line, then the slope of that tangent line will give the instantaneous velocity at the time at which it is tangent. So at time ta in this little graph that I've drawn here. All right. So that basically is how acceleration works, what it is, what it does. It is a rate change of velocity. Note that the acceleration need not be in the same direction as the velocity. An object can be moving in one direction and accelerating in the other. That basically just means the object is slowing down. And in 2 dimensions, the object and motion and velocity and acceleration may not even be collinear. For example, in uniform circular motion, the acceleration vector will be perpendicular to the velocity vector at all times. All right. So to make a little list, acceleration versus velocity need not be in the same direction or even collinear. But if they are collinear, then it means the object's either speeding up or slowing down. So same direction essentially means that you have a velocity like this, and you have an acceleration also like this. Opposite direction would mean something like the acceleration points in one direction, but the velocity points in exactly the opposite direction. So this would be speeding up, this would be slowing down. By the way, it doesn't matter which direction the two happen to be in. This also is speeding up, but in the opposite direction. This also is an example of slowing down. Okay. So the other possibility is that the velocity and the acceleration are not collinear at all. So anytime that it's not collinear, the object is basically turning. So this right here is a little example of motion on a circle. The object maybe is moving about this little black dashed line circle. The green arrows give instantaneous velocities at different points in time. The purple ones give instantaneous accelerations at that same point in time. Note that the two, in this case, are perpendicular to each other. It doesn't have to be perpendicular. Motion on, say, an ellipse, like what the planets do in their orbits, you have a very nearly perpendicular if the circle is if the ellipse is near circular. But there's some component along and some component perpendicular to the velocity. But that's getting into two-dimensional motion. The point here is the acceleration does not need to be in the same direction as the velocity, although the two may be in the same direction. On that note, let's consider a simple example. We have an object which is moving in the positive x direction, for example, due east. And it has an initial speed of 1 meter per second, and after 2.5 seconds, it has a speed of 4.75 meters per second. So we want to know what's the average acceleration. So basically this right here and this right here represent initial and final values for the speed, and given a direction, they could in fact be initial and final velocities. So we might say like v initial is plus 1.00 meter per second, and v final is plus 4.75 meters per second. This number right here represents the time that has elapsed. Now, our definition for average acceleration says that it should be the change in velocity per time, and change in velocity just is the final minus the initial velocities divided by delta t. So we would have 4.75 or positive 4.75 meters per second minus positive 1 meter per second, all divided by the time, which is 2.5 seconds. Now this ends up being on the top 3.75, and so that gives me an acceleration of 3.75 divided by 2.5, which I believe is 1.5 meters per second squared, 2 sig figs. So that would be your average acceleration.